Welcome to the 18th session on group theory, and today's session we shall continue what we started yesterday, namely the left translation map G going to A times G, where A is fixed element of the group. Okay, and after that we will talk about cosets, and there is a lot of things we will do it. Okay, so yesterday what we did was G a group. Well, let me just change the color now. Group A and G. Okay, then we define lambda a map from G to G, defined by lambda a of G equal to A times G. This we call it left translation by A. Right? We saw lambda a is a bijection. That means it belongs to S of G. Right? Set of bijections. Right? Therefore, we had a map phi which is from G to S of G, where A go into lambda a. Right? Since this is a group, this is also a group under composition. So I have a natural map. So my question is phi a homomorphism? We saw yes. The answer is yes. That's very easy because phi of AB is lambda AB. But what is lambda AB acting on G? That will be AB acting on G. That is A acting on BG. But that is A acting on lambda B of G. But that is lambda A acting on lambda B of G. This means lambda A composite lambda B acting on G. Therefore, we showed that this is equal to lambda A composite lambda B. Okay, pause, review, proceed. So if you are a BSc student, these are the places where you start having difficulty. You already have problem with the group. Now we are looking at the group and then symmetry group of the group, namely set of bijections on G, and then we are taking an element, group element, going to some bijection of G. Okay, unless you revise it once or twice, you will never become comfortable. Okay, this is what I call the second order. First order is sets. Then we are talking about functions or maps of sets. Okay, this is always a second order, so please review that. Okay, don't quickly. Whenever there is a PRP, be very sincere. Even though I may keep talking, pause the video, go back and review it. As I again said, don't try to remember anything, just to review, keep reviewing. Slowly you will see you can do mathematics on your own without me. So let me go to. Now the next question is, therefore, is this 1 1? Okay. Note that I may want to know whether it's an isomorphism. Is an isomorphism? Because it's already a group homomorphism, therefore I can ask it's an isomorphism. But then you should see, suppose mod G is n, then S of G is all bijections. Okay, that will be n factorial because it is like S of Sn, right? There are n elements, therefore it's all permutations of n elements. So that is n factorial. So that's a very large. Therefore, there is of course unless n equal to 1, it's never isomorphic. Do you understand this? I'm making life easy so that every time you keep reviewing the concepts, review the concepts. Okay, is this 1 1? Now notice that phi from G to S of G is a homomorphism. It's already group homomorphism. So when I want to say phi is 1 1, there are two ways of showing. That is, if I take A not equal to B, I can show phi of A equal to phi of B. Now phi of A is not equal to phi of B. Or if phi of A equal to phi of B, I can show A is B. These are the two ways to show phi is 1 1. Is that right? For any, right? If F is a map, from x to y. This is 1 meaning if x1 is not equal to x2, f of x1 not equal to f of x2, or if f of x1 equal to f of x2, that implies x1 equal to x2. These are the standard ways in set theory. But then remember, phi is just not a map, it is a group homomorphism. We have seen a group homomorphism is 1 if only if the kernel is trivial. Do you remember that? We are going to use it. So enough to show, enough to check the kernel, enough to identify the kernel of phi. Okay, now when is, okay, phi of a is identity. This is the identity of s of g, right? What is phi of a? That is a lambda a. That means if it's identity, when lambda a is identity, that is true if and only if for every g in g, lambda a at g should be equal to identity that g, but this is g, but this is ag. That means for every g, ag must be equal to g. In particular, when g equal to identity, then I get a equal to identity, right? Therefore, phi of a is identity if and only if a is identity. That means therefore phi is 1. Okay, again pause, review, proceed. Okay, now notice that we used extra information. Phi is, I can directly prove phi is 1, but we used extra information to prove phi is 1 by identifying the kernel, because phi is a group homomorphism. These are the small things which you have to master, learn. Okay, now what do we have? I have map G into S of G, which is a 1 homomorphism, right? And remember, if F from G to H is a homomorphism of groups, then F of G is a subgroup of H, right? Therefore, phi of G is a subgroup of S of G. Is that clear? Right? Now, therefore, I can think of this as a map from phi from G to phi of G, which is of course contained in S of G, right? Whenever f is a map from x to y, if f of x is equal to b, which is the subset of y, then I can think of this as a map from x to b, right? We denote the same f, it's okay, right? Are you following? This is why you should always look at foundations. Okay, right. Anyway, come back, right? Now, what kind of a map? Remember, this is a subgroup, and hence is a group, and the phi is a 1 on to homomorphism from G on to phi of G. Therefore, phi is phi from G to phi of G is an isomorphism. Right? Both are groups, and they are now isomorphic groups. Okay. But what is the importance of phi of G? Phi of G is a subgroup of S of G, which is a symmetry group. This is what you call symmetry group. Do you remember? For each x, a non-empty set, we define S of x under composition is a symmetry group. When x equal to 1 to n, then we call it symmetry group of n symbols 1 to n. This is a special case of this. Is that clear? Therefore, this is, so we have proved what is known as Cayley's theorem. Let me just make sure that I have shared the screen. Yes. What does it say? Let G be a group, then okay, G is isomorphic to a subgroup of the symmetry group S of G. This is what we proved. Okay, pause, review, proceed. So you may think it looks like too abstract, but let's try to understand it. Suppose my group G is finite. Okay, call it the elements of G to be G1 to Gn. Of course, identity will be there. Maybe can't G1 may be identity. I don't care. Let me call it G1 to Gn. Right now, fix an element A in the group G. Right. What now? S of G. What does it mean? It is the set of all bijections of these n elements G1 to Gn. Are you following? Let me look at a special case. We will understand this better. Suppose G is finite. Okay. G1 to Gn. Okay. And fix A equal to some Gi. Then what is lambda A? Lambda will map Gj to Gi Gj. Since this is a bijection, notice that therefore this is again what will I have will be G1 sorry Gi G1 Gi G2 Gi Gn, but this is same as G1 to Gn. As such they are the same. That means you can think of this. I will write in place of G1 I will write G1 G2 Gn, then Gij is this will be some element then, right? That will be I will call it, let us say something I1, and the next one I will call it I2, and this is called In. You understand that? Okay, please take time. Right? Okay. So if you want, let me just look at again a simple example. Suppose my G is GZ3. So it has three elements 0, 1 and 2. This is my G1 and G2. This is G3. Right? Now let us look at, okay, my A equal to let us say G1. Then what will happen? 0 plus G1 1 and 1 plus 1, that will be second element, and 2 plus 1, that will be third element, 2 plus 1. But this is nothing other than 1, 2 and 0. That means my 0, 1, 2, maybe I will instead just make ideas clear. Instead of that, let me write Z3 as 1, 2, 3. My 3 is 0, remember? Okay, don't get confused. Okay, therefore you will clear. Okay, my G1 is my 2. Okay, G1 is 1. Well, let us say G1 is 1. Then what happens? 1 plus 1 and 2 plus 1 and 3 plus 1, that will go as 2, 3, and that is 0, or sorry, keep it as 3, and then 4, 4 which is 1. Right? Therefore my 1, 2, 3, when does 2, 3, 1? So this is a permutation. Yeah, therefore my lambda G1 it stands for this permutation 1, 2, 3 going to 2, 3, 1. Okay, pause, review, proceed, try to find out what is lambda G2, where G2 is my 2. Okay, so that you will understand. Right? Therefore, when G is n, what this says is G is isomorphic to a subgroup of Sn, because S of G, when I identify G with 1 to n, just a bijection, my Gi go to I, right? Then you can find out it is a subgroup of bijection. That's the example which I worked out. Please understand. So what Cayley's theorem says, any group is going to be isomorphic to a subgroup of symmetric groups. Yeah. So it looks as though that if I understand symmetry groups, that's good enough for group theory, right? But that's not that easy. Why it's not that easy? Let us just look at. Suppose G is a group of 6 elements. Let's say Z6. I understand it much better, right? Z6 is very easy. But it is going to be a subgroup of S6. But S6, how many elements are there? 6 factorial. So if my arithmetic is correct, 1 times 2 times 3, 24, 24 times 5, 120, 720 elements. I have to search for these 6 elements as a permutation, okay, permutation set of permutations in 720 elements. Just imagine how difficult it will be. Suppose it's a subgroup of, it's a group of order 10, it will be 10 factorial O2. It is like finding a needle in a haystack. You know that? What is meant by haystack? After you thrash like a wheat or rice, then you feed it right to the cattle. That's a haystack. In that you put a small needle, huge haystack. Do you find it? That's what it means. So it's a very good theorem. It has its own uses, but in some sense it's not a very practically right to search for the subgroup inside S of n. If n is even moderate, even n is 6, we already said it's very difficult. Okay. Right. Now come to the most important thing. In my kind of enthusiasm, I forgot when we dealt with isomorphisms, I forgot the most important result. Okay. Right. I will talk about it. The result is, in fact, we had already seen it. Suppose we have seen if so G is a cyclic group of order n, and then we set up, you remember, we set up a group homomorphism set Zn to G. Yeah. That is actually 1 1 and on to, therefore Zn is isomorphic to G. That means if G is a cyclic group of order n, G is isomorphic to Z mod n, Zn. Okay, I'll do it. So this is a very important result. Okay, I should kick myself. I forgot to do that yesterday. Okay, what is that? Suppose G is a cyclic group. Say G equal to A. Right? Let us say of order n. Right? Then we set up a map F from Z mod n to G. How did you do? Start with any k here, send it to A power k. And we checked it's a group homomorphism. Why? Because you start with any element, okay? Because what are the elements here? 0, 1 up to n minus 1. They will go to 1, that is identity a to the power n minus 1. That's a group homomorphism, because if you have R and S in Z mod n, right, where will it go? F of R plus S will go to a to the power R plus S, correct? But what is R plus S? R plus S equal to T, okay, where okay, T lies between, let me write, R plus S equal to some Q into N plus T, 0 less than or equal to T less than N minus 1. This Q has to be at most 1, because remember R is less than N, S is also less than N, R plus S will be strictly less than 2N. Therefore, it will be at most, my Q has to be 0 or 1. But that is immaterial, write it that way. Therefore, R plus S is nothing other than T. This is same as F of T. But this is also A to the power R plus S, that is A to the power Qn plus T, which is A to the power N Qn into A to the power T. A to the power Qn is identity into A power T, that is A power T. Right? That is A to the power R into A to the power S. Okay? So, this F is an isomorphism. So, what is the takeaway? So, the important result is any cyclic group order meaning number of elements, order n, is isomorphic to because by this, okay, please remember we are using law of exponents. F of r plus s will be a power r plus s, but r plus s is f of t, then a power r plus is same as a power r into a power s, that is also a power t. Okay, please revisit the earlier example, yeah, to master this. Okay, now suppose G is an infinite cyclic group. This is P or P. Suppose G is cyclic but infinite, right? So let's look at A equal to A, but then this is A power n and n is over z, and all A power n's are distinct. That is A power r equal to A power s if only if r equal to s, right? Now again the same map we have from now z to G, n going to A power n. This is the group homomorphism, which is an isomorphism, right? Therefore, up to isomorphism, this is what one usually say, up to isomorphism. Let me write it. This is the word you will keep hearing, algebraists will use it. Up to isomorphisms. Infinite order. Namely, any cyclic group of order n must be isomorphic to Zn, and any cyclic group of infinite order must be isomorphic to the additive group of this. Okay. Pause, review, proceed. Okay, I hope you understand this. So with this, I will stop isomorphisms, results are related to isomorphisms. There are a lot of things which you have to do, but one has to stop at some point. Okay, it's not going to be encyclopedic lectures. It's only to initiation into thinking abstractly, especially in algebra. Is that all right? Okay. Next, we want to talk about the new different concept. Okay, it's a completely different from the what we have seen in the last 1.5 hours. This is something different. What we want to talk about is the cosets. That remember, that's the second part of the today's title. So what is that we want? So let G be a group, H is subgroup of G, right? Then remember when F, just this is a recall F from G to H, these are all groups, not subgroups, these are different groups. Okay, this is a homomorphism. Then we looked at kernel of F, call it K, that is a subgroup of G, right? Then we saw this kernel allowed us to look at what are the elements G in G whose values is f of a fix. Okay, suppose fix h in h, assume that f of a equal to h. Okay, therefore f of h. Then we found out this is nothing other than, okay, a times h. Yes, sorry, a times k, which is also k times a. Do you recall this? Right? So these are called cosets. This is what you want to look at today. So let H be a subgroup, okay, and let A belong to G. Then we define A of H. Okay, I am back in this question, this place. I am assuming H is a subgroup of G. Let A be an element. Then this is the set of A times H, where H is in H. You understand that? Yeah. Right. So let us try to look at a specific example. Suppose my G, this is called a left coset because A is on the left coset of H with respect to A. That is by left multiplication by. Let G equal to Z, of course under addition. My H equal to, let us say, n times Z. Let us assume n is greater than or equal to 2, natural number. Right? Now, sir, let me assume some specific example. Let me take n equal to 6. 6 times Z. Right? Now, let me take A equal to 10. Okay? Make it A equal to 7. Okay. So, what is AH here? Remember the binary operation addition here. Therefore, it is, I will write it as A plus H. Okay, A plus H is set of all A, which is 7, plus H, which is multiples of 6. Therefore, 6n as n varies over Z. Don't forget this n. Okay, this is what it is, right? Therefore, what does it mean? So, H, what is H? H consists of 0, 6, 12, etc. minus 6, minus 12, etc. Therefore, 7 plus H is what I am looking at. That is going to be, you add 7, you add 6, plus 7, 13, you add this 7, 19, etc. You add 7, you will get a 1, you add 7, you will get minus 5, etc. Right? But do you recognize this? See, these are the examples one never looks at. Okay, one immediately goes to prove lot of results about cosets, but as students should get to know how to work with that, what it is, what kind of object I am dealing with. Okay, that's what we want to understand, right? Okay. Notice that this is nothing other than, suppose you start with any element 7 plus 6n, I can actually write it as 1 plus 6 plus 6n, therefore it is actually 1 plus 6 times n plus 1. That is 1 plus some 6 times m, some integer, I don't care. Right? Any element here can be written as this. Now you see that. Therefore, a plus h, that is 7 plus h, is same as 1 plus h. That is, look at all these elements. When you divide by 6, they all leave remainder 1. Right? 13 divided by 6 will really have remainder 1, 18. And minus 5 will be 1 plus minus 1 times 6 plus 1, because I have minus 6 but I want only minus 5. And similarly, this will be minus 11. Minus 11 will be minus 2 times 6, but it's minus 12, therefore I have to add 1. You understand? Therefore, this is the set. Yeah. Therefore, so what do you understand now? Right? So any coset, okay, a plus 6z is actually r plus 6z, where r is between 0 and 5. Okay, pause, review, proceed. So what is interesting here? The group G is Z which is infinite, the subgroup H is 6 times Z, which is again infinite, but I am looking at cosets as A varies over all integers, right? A could be any integer. Therefore, how many cosets I will have? A plus 6Z. As A varies, you may think there exists infinitely many cosets, but how many cosets are actually there? There are only 6 cosets. Coset 0 plus 6x, 1 plus 6x, and 5 plus 6x. That's it. Isn't it interesting? Yeah? Right. You also have an idea about cosets, right? Now let's look at the cosets. There is something lot more you can learn. Take two distinct cosets, right? Therefore, one coset will be something like say 1 plus 6z. The other coset will be 4 plus 6z. Can they have any point in common? They cannot, because any element in 1 plus 6z leaves 1 as the remainder when divided by 6, whereas any element in 4 plus 6z leaves 4 as a remainder when divided by 6, right? By the division algorithm, the remainders are unique. Therefore, they are always distinct, right? They don't have any point in common. That's the most important thing. Yeah. So let us observe. No point in common. Okay. Let's look at one more example. Okay. Now let's look at one more example. This example was integers. Therefore, what are the cosets now? The cosets are nothing other than the congruence classes we had already seen. Do you remember what was our definition of Z mod Zn? Zn is has only 6 subsets of integers, which are the one which all leave remainder 0. Then the second subset is all elements which leave one as the remainder. Then all integers which leave n minus 1 as the remainder. There are only such. That's how we wrote. So the cosets are nothing other than the elements of Z mod Zn. Yeah. Don't get confused. Just try to think. Slowly you will get used to this. Okay. Right. Now I want to give a geometry example. I have a lot more geometry example, but I will stop give only one more so that I can get along with the theory. Okay, now let's look at another example. Okay, this is geometry example. Let's look at R2 with addition. That is, if I have x1, y1, x2, y2, then addition is x1 plus x2, y1 plus y2, right? So this is a group. Now let's look at H to be the x-axis, namely x comma 0, x varies over R. Then H is a subgroup of G. All these things you had already seen, right? Remember, whenever V is a vector space, it has two operations. If I look at only this pair, then this is the abelian group. We had already seen it. I am just looking at special example, right? Now suppose you start with something like, let's say, so let us try to think of this geometrically. This I will draw in a thing. This is my H, which is y equal to 0, right? Now let us start with an element A in G, call it A equal to, let us say 1 comma 1, right? Then I want to know what is, now remember what is AH here? It is addition, therefore it's 1 1 plus H, right? So what is A plus H in this case? That is 1 1 plus set of all elements x comma 0 as x varies over R. This is going to be, how do I do that? Remember what is AH? A times H as H varies over. Therefore I have to take 1 1 plus x0 as x varies over R. But what is this? This is x plus 1, 1 as x varies over R. Now notice that x plus as x varies over R, x plus 1 will vary over R completely, right? That is, if you give me any y in R, okay, let us say x dash in R, okay, I can find an x dash minus 1, take it as an x, then what will be x plus 1? X dash minus 1 plus 1 will be x dash. Therefore, this is the same as x dash 1 as x dash varies over R. So, what is this? This is geometrically this line. So, more generally, suppose I take a point A, call it alpha beta in R2, right? Then what will be A plus H? That will be alpha beta plus x0 as x varies over R. This is same as you will see x dash comma beta where x dash varies over R. Therefore, it is this. So, this is y equal to beta line. This was y equal to 1 line. Yeah. So, what are the cosets here? They are all lines parallel to the x-axis. Namely, okay, therefore any coset is given by y equal to beta, that is set of all x beta, that's it, as x varies over R. These are the cosets. Pause, review, proceed. Yeah, now do you see something interesting? Again, take any two cosets, they are all distinct because either they coincide or they are all parallel lines. Okay, distinct parallel lines. Do you understand that? Like what we saw in the earlier case. There the cosets were congruent classes. Okay, with remainder 0, with remainder 1, with remainder n minus 1. These are the congruent classes. So take any two equivalent class there, any two cosets, either they are the same, any two meaning any two. Okay, not necessarily distinct. Okay, some coset by R, coset by S, then either the coset by R equal to coset by S or they are disjoint. Similar thing here. Okay, that's what we want to prove. Okay, I gave one number theoretic example, one geometric example. Please review. These exams are never done usually in classes. Please look at them. Right. So what have we done? Given a group G and a subgroup H, we define what are meant by cosets. Okay, is the concept AH clear? How we arrived at it? That's why I took a lot of things. Even under multiplication also I can do that. Perhaps I will do that just for quickly. I won't spend much time. A third example. Okay, suppose G equal to GLNR. Okay, if you don't want 2 by, take n equal to 2, 2 by 2 invertible matrices. Okay, then H equal to set of file elements A in G, so the determinant of A is equal to 1. We know H is a subgroup of G. Now what are the cosets? Cosets are given by, okay, AH, fix A in G, the coset, this is the coset, left coset. This is a set of all A times B, where B varies over H. Right? Is that clear? Right. The multiple here is the matrix multiplication. Right? Now I want to identify this abstractly. At least describe this coset abstractly. It is just a listing. Okay. How do I do that? Suppose C belongs to AH. That means what? C is the form AB. Then look at that. Determinant of C is determinant of AB, but that is determinant of A into determinant of B. That is equal to determinant of A because this is 1. Right? Therefore, A is unfortunate. Both are capitals. Okay. Maybe I should have chosen element of a matrix as A. Then it will be easier for you. Anyway. Okay. This is contained in this subset C in GL and R, such that determinant of C is same as determinant of A. But I want to say this equation also true. That is, I want to say these are equal. Okay, this is a multiplicative example. Let us look at it. Suppose you give me C. Okay, here. Right? Then what do I want? I want to write it as AH. That is, I want to say C belong to AH. That means what? I want to write C equal to A times B for some B in H. Is that clear? Please understand. I want to say it belongs to this, an element of this H, AH, but an element of AH is of the form A times B where B is in H. That is determinant of B is 1. Right? So can I solve for B? Yes. Because remember these are all invertible. Therefore multiply by A inverse C, that is equal to B. Right? So I solve for B. But am I through? No. Because I have to ensure this is of course an n cross n matrix, but I have to ensure this B belongs to H. That is, I have to show determinant of B is 1. But what is determinant of B? That is determinant of A inverse C, but that is determinant of A inverse into determinant of C, but that is determinant of A inverse, that is 1 by determinant of A into determinant of C. But remember, determinant of C is determinant of A, therefore it's equal to 1. Right? So what we have done is, if A is in GL and R and H, this is what we call SL and R, determinant 1, okay, then AH is nothing other than set of matrices in GL and R whose determinant is determinant of A. That's it. We have a beautiful characterization of cosets. Right? Again, you see that if you take two distinct if you give two cosets, some let us say AH and BH, what happens? All of the elements in AH will have determinant A and all of the elements in BH will have determinant B, right? So what happens? So either they are the same or they are distinct. Yeah, please go through, understand, look at these three examples. These kind of exams are usually never done, okay, in the classrooms. Please go through them. So how much time do I have? Another 15 minutes. Okay, I think there is enough time. Let us go through that. In screen mode. Yeah. Now shall prove whatever we have been looking at. Okay, so return to the general setup. So here G is a group, H is a subgroup, and A is an element of G. Notice that when I look at AH, the first thing you should notice is A belongs to GH. This is the first thing you should always notice, keep it in mind. Why is that? Because H is a subgroup, therefore E belongs to H. Therefore A times E must belong to AH, but A times E is A. Yeah? So this is a very crucial observation, keep remembering this. A always belongs to AH. Okay. The next thing I want to know is, earlier we saw when AH equal to BH. For example, in the case of Z and NZ, okay, you gave me something R plus NZ, S plus NZ, okay, these are two coses. When are they equal? I want to understand. They are equal if only if R, okay, and S leave the same remainder when divided by N. That is same as saying R minus S, okay, N divides R minus S, R is congruent to S mod N. All are equivalent statement. Okay, that is why you should learn elementary number theory before coming to group theory, abstract algebra. Okay, I want to understand. And similarly, let's look at in the second case R2. Okay, suppose I have an element AB in R2. Okay, and CD another element in R2. Right? Then when is A plus, and what is my H? My H is x-axis. Then A plus BH, when is it equal to C comma D plus H? We found out this is nothing other than B plus, okay, 0B plus H, and this is 0D plus H. That means every element here has the y coordinate B, every element here has the y coordinate D. Therefore, if they are equal, B must be equal to D. Right? And similarly, in the next case, GLNR case, okay, what did you have? When is AH equal to BH? That is equal to determinant of A equal to determinant of B. Because all elements here have determinant A, all elements have determinant B. If they are equal, that means determinant A is determinant. You see that? This is the kind of characterization I want to understand. So general setup. When is AH equal to BH? Okay. Suppose this is true. If, okay, assume. Then A belong to AH. Therefore, that implies A belong to BH. But when A belong to BH, what does it mean? Any element of BH is of the form B times H. Therefore, there exists H in H such that A equal to B times H. Right? That means B inverse of A equal to H. That means B inverse of A belong to H. Yeah. Since H is a subgroup, B inverse of A inverse, that is A inverse B, that also belong to H. Right? Therefore, this happens if only if A inverse B, B inverse A belong to H. Pause. Not if only if, sorry. It implies this. This all we proved. Alright. Okay. Now, this is something very interesting. Okay. See, I keep learning mathematics not as simply as an isolated subject. I try to understand with something which I already learned and compare and contrast. That way, you become confident about both the results. Okay. Now, what have we shown? I took a subgroup H of a group G and I have two cosets AH and BH. I want to know when they are equal. If they are equal, I proved a necessary condition, namely A inverse B must be in H or B inverse A must be in H. Is that clear? Yeah. If the converse true, I will prove that and come back to this. Okay, the analogy. Okay, let me prove that so that we will get rid of it. Conversely, let's assume A inverse B and hence B inverse A belong to H, right? Then we want to claim AH equal to BH. Okay, let's look at it. There are two ways of doing. Okay, so let us prove AH is contained in BH first, right? So start with an element here, it is AH. Okay, AH belong to AH, right? I want to say it belong to BH. That means there exists a H1, so that it must be of the form this is AH, this is BH1, right? Is that clear? Yeah. So there are various other ways of doing, but since I started, let me finish it. AH is BH, right? Now, what is unknown? I have to understand what is H1. Yeah, but multiply both sides by B inverse. B1, sorry, H1 is unknown, right? I want to say this. That means there is the H1 in H, so that AH must be equal to BH1. So H1 is unknown, but can I find H1? Yes, it is B inverse A H is H1. If such a H1 exists, it must be this. But what do I know? B inverse A belong to H belong to H. Therefore, this product belong to H. Therefore, H1 belong to H. You understand that? So, what I have shown is, I start with any element AH in AH. I want to prove AH belong to BH. That means I have to find a H1 in H, so that AH equal to BH1. Okay. What is that H1? My H1 is B inverse A into H. Is that clear? Or review proceed. Therefore, we proved AH is a subset of BH. So similarly, BH is a subset of AH. Exactly the same way. Start with the BH. I want to know whether it is AH1. Therefore, what must be my H1? A inverse BH. Is that clear? I just went through quickly. Pause, review, proceed. So, what you have proved is AH equal to BH if and only if A inverse B and B inverse A belong to H. If one of them belong to its inverse, the other one is the inverse, therefore it has to be in H. Okay. Third thing is, suppose B belong to AH, then I claim the cosets defined by AH equal to BH. Yeah, before that I will go back to my analogy. We'll return later. So AH equal to BH if and only if A inverse B and B inverse A belong to H. Does this remind you of something? Yesterday, when we did something about the importance of kernel, I looked at the linear system of equations. Do you remember? Suppose I have a linear system. I will write it in matrix form. Ax equal to B. B is a column vector. X is a column vector. A is a corresponding matrix. Okay. X equal to B. Then what did you find? Suppose alpha equal to alpha 1 to alpha n, a column vector, is a solution. That is A alpha equal to B. Right? You understand? See, right? So let us assume A alpha 1 equal to B. And suppose A alpha 2 is also equal to B. There are two solutions of the non-homogeneous system. Then what do you know? Alpha 1 minus alpha 2 is solution of the homogeneous system. Right? Do you remember? When you looked at the kernel, I said H is something like the solution set of the homogeneous system, and AH or HA is the something like solution of the inhomogeneous system, where it is set of all G such that f of G equal to f of G. Okay. I am making mathematics difficult? No, I am making mathematics the intrinsic deeper aspects I want you to appreciate. Okay, don't just learn by what is given us at class notes. Okay, right? Therefore, this one reminds me of AH equal to BH. That means what? The solution set AH and the non-homogeneous solution set BH are the same if one, okay, they represent the same solution if one only if A inverse B is the null solution. Something, okay, vague, but please understand. Okay, now come to the next one. Okay, the next one is, suppose B belong to AH, right? That means B equal to AH for some H. There exists H in H. That means, okay, A inverse B equal to H. That means A inverse B belong to H. That means AH equal to BH. Right? Are you following? Yeah. Right? B belong to AH. That means there is H such that B equal to AH. Right? So multiply by A inverse, that is A inverse B is H. That means this, right, only this is also if only because AH equal to BH if only if A inverse B belong to H. That is if only if there exists H such that A inverse B equal to H. That is if only if B is AH. That is if only if B belong to AH. You understand this? Therefore, B belong to AH if only if AH equal to BH. Okay, I will stop with an analogy. Let's look at R2. Okay, and my H equal to x-axis. Right, now let's look at this. This is my H, this is my AH. Right, suppose my B belong to this, then what is B plus H? Then this is also B plus H. Why? What does this mean? A plus H simply means a line passing through A parallel to H, and B plus H also means a line passing through B parallel to H. They are the same. Because B already belongs to this, therefore the only line which passes through B parallel to H is this line, A plus H. Therefore they are equal. Okay, think about, okay, this kind of geometry is never done. Okay, and as usual, those who are asking me to do group theory, many of you might, okay, maybe wondering why did you ask me, right? you expected some kind of cut and dried easy algebra, but you see I am making it more interesting, hopefully. Okay, if you don't give up, just don't say that it was not done in my class, so it will not come for exams, then you, okay, you may be able to pass exam with flying colors, but you may not appreciate mathematics. Yeah, I hope you enjoyed this. Okay, the best way to keep you motivated about my lectures, as I keep saying, is watch it with a few friends. Okay, it's like going for physical, let's say walk for every day, going to the gym every day. If you go alone, you may lose motivation. But if three or four of you go together for walking, cycling, swimming, or going to gym, okay, one of you may feel, oh, I don't want to go, but other people will motivate you to join them. So the spirit is alive, the motivation is kept alive. The same way, please watch my videos not alone, with few friends. At each and every PRP, stop it, okay, and discuss with your friends. Then you will see how much of mathematics you learn, and more importantly, you will learn you will appreciate maths, and you will be confident, and you will be able to do mathematics on your own. That is the aim of my video series. Okay, not to make you pass some exams. Okay, I hope you enjoyed. We will meet again. Thank you very much.